Good morning everyone, my name is Caterina Amendola and I'm a second year PhD student from Politecnico di Milano. First of all, I would like to thank you for giving me the opportunity to share with you our work on the accuracy of time domain near-infrared spectroscopy in measuring newborn cerebral hemodynamics. Brain injuries are one of the major causes of morbidity and mortality in neonates, and because of this reason it is extremely important to have techniques that allow for monitoring brain activities in neonates. Nowadays, the most used monitoring techniques are positron emission tomography, magnetic resonance imaging, and xenon clearance. However, these techniques are invasive, bulky, need patient transport and mobility, and some of them are radioactive or toxic. In this scenario, near-infrared spectroscopy techniques seems to be a good alternative for non-invasively monitoring cerebral hemodynamics at bedside. Near-infrared spectroscopy techniques are based on the concept that light in near-infrared region could penetrate a few centimeters inside biological tissue because of the very low absorption coefficient of the main tissue constituents. Among all near-infrared spectroscopy techniques, Time Domain NIRS exploit laser pulses of 100 of picosecond of duration and analyzes the re-emitted pulse, in particular by fitting the distribution time of life of the re-emitted pulse with the diffusion approximation of the radiative transport equation. It is possible to retrieve the absolute value of the absorption and reduced scattering coefficient, and from them to estimate the absolute value of deoxygenated and oxygenated hemoglobin concentration, and from them total hemoglobin, which is the sum of the two, and saturation. However, as we can see from this picture, light should pass through many different tissue types before reaching the brain, which are scalp, skull, and cerebrospinal fluid. Those upper layer could influence the estimation of hemodynamic parameters. Moreover, as the head is not flat, and its geometry could affect the estimation of hemodynamic parameters. So because of these reasons, we decided to determine the accuracy of time domain near-infrared spectroscopy in measuring cerebral hemodynamics in case of neonates. In order to do it, we used a mesh-based Monte Carlo tool for simulating photon propagation inside realistic catalysis of 29 and 44 weeks post-menstrual age meshes of neonate's head. The head structure was divided in three parts: the extracerebral tissue, which is comprehensive of scalp and skull, the cerebrospinal fluid, and the brain. These three tissue types are characterized by different optical properties. We decided to simulate light propagation at 690 nanometer and 830 nanometer in order to be able to determine the hemoglobin concentration. The detection was positioned in the AFP7 position of the 1020 International System of EEG, and the injection 15 millimeters away along the scalp surface. Moreover, in order to be the more realistic as possible, we decided to take into account also the intersubject variability of optical properties and to repeat all simulation by increasing and reducing of the 25% the optical properties of the extracerebral tissue and of the brain. Then we changed the absorption coefficient of the brain to model three common pathology in neonates that are ischemia, hyperventilation, and hypercapnia. Then the simulation results were analyzed with two models. The semi-infinite homogeneous model, in which we consider the head as a semi-infinite slab, and the spherical homogeneous model, in which we consider the head, the neonate's head, as a sphere of radius equal to the half of the distance between nasion and inion. In the end, the estimated results were compared to the values simulated in the brain, and so the mean average percentage error was computed. Here I reported the results in case of ischemia, both for semi-infinite and spherical homogeneous model. The gray line represents the total hemoglobin and saturation values simulated in the brain. The red and the blue line represents the one estimated by semi-infinite homogeneous model and spherical homogeneous model, whereas the shadow represents the range of variation of the estimated values because of the intersubject variability. So, as can be observed from this graph, the total hemoglobin estimated was lower with respect to the one simulated in the brain, and the underestimation is higher in case of spherical homogeneous model. Whereas in case of saturation, the values estimated both for 44 weeks and 29 weeks postmenstrual age meshes are near to the one simulated in the brain. And we can observe that in case of a spherical homogeneous model, the variation of saturations of the brain are better estimated. Indeed, the angular coefficient of the linear regression curves that fits the saturation in case of 29 weeks reach almost 1. In case of hyperventilation, the same consideration previously done holds true. And in this case, we simulated a constant total hemoglobin in the brain and an increase of the saturation from 70 to 100%. In this case, so in case of an increase of saturation, the variation is better estimated. In case of hypercapnia, instead, we simulated an increase of total hemoglobin in the brain and a simultaneous reduction of saturation from 70 to 40%. In this case, we can see that the total hemoglobin variation is underestimated also in this case, and this leads also to a worse estimation in the saturation variation, and in this case we obtain an angular coefficient of the linear regression curve which is much lower with respect to the previous case and reach 0.67. So, as a conclusion, we can say that time domain NIRS allow for non-invasively monitoring neonates brain haemodynamics at bedside, and we observed a good accuracy in estimating the brain saturation with a mean average percentage error always lower than 20. Whereas in case of concentration of deoxygenated hemoglobin, oxygenated hemoglobin, and total hemoglobin, we observed an underestimation and a mean average percentage error that reached the 50. The saturation variation finally were better retrieved with the spherical homogeneous model with respect to the semi-infinite homogeneous model, and the angular coefficient of the linear regression curve that fits saturation variation reach almost 1. Thank you for your attention.